Okay, so problem 1.47 is about this molecule called allene. So let's look at allene here. Allene is somewhat unusual because it has two adjacent double bonds, and that is true. This is a little bit strange, but it's relatively straightforward. The question is, what does this molecule look like? What's the hybridization? What's the shape? And it turns out there's something a little bit surprising about allene when you really look into it. And it all has to do with the fact that this is an sp hybridized atom in the middle, and these are sp2 hybridized. So we can tell because this carbon has three things attached, 1, 2, 3. The central carbon has two things attached, 1 and 2, so it's sp hybridized. And then this one also has three things attached, so it's sp2 hybridized. Now, let's just start in the middle. If the middle carbon is sp hybridized, remember you have in sp hybridization, you have an s and your p orbitals. You have your 2s orbital and your 2s and 2p, and you have your 2p orbitals. Remember, there's 2px, 2py, and 2pz. So when you have sp hybridization, you are mixing the s and one of the p orbitals, and that leaves you with two pure p orbitals. And if we look at just the pure p orbitals here in the middle, remember there's one p orbital. Let's just call that pz. And then let's do another one in a different color. The other one is orthogonal, meaning it's coming out and going back. So let's call this, so here's py and here's pz. Now, when you have an sp hybridized carbon, so if we look at the next carbon on the right, this one here, it has a p orbital, and let's just look at that. If you have sp2 hybridized, and this is the s. sp2 hybridization means you have the s and then two of the p orbitals. So this is sp and this is sp2 hybridization. sp2 hybridization. And that leaves you, sp2 hybridization leaves you with one pure p orbital. And so if we look at the one pure p orbital in this sp2 hybridized carbon here, the one on the far right, that puts this into a good orientation to overlap. And I'll draw some electron density here on the top and the bottom. So that gives us sort of this pi bond overlap and between the two carbons. And then if we have this carbon is sp2 hybridized, that means that the two hydrogens attached and this middle one, so if we look at this bond in the middle there, this bond in the middle is in the board or in the plane of the screen or the paper. That means that this hydrogen has to be going back, and this other hydrogen, to be in the plane, has to be coming out at you. Okay, so these are all in a plane. This is the trigonal planar geometry of an sp2 hybridized carbon, which has this pi bond, pi overlap, above and below the plane formed by the three substituents, the three other groups. Okay, so let's look at the other carbon on the left end. It's got a similar situation, but it's one pure p orbital. The other carbon, its p orbital, in order to overlap with the central carbon's remaining p orbital, it p orbital has to be coming out at you and going back into the plane of the board. So this bond here, and remember the sigma bonds, the bonds in the middle, the sigma bonds, are due to the overlap between the sp and the sp2 orbitals. But right now we're just talking about the p orbitals. We're talking about the pi bonds. And I'll just draw that pi, or that sort of electron overlap. Now this electron overlap for the pi bond is coming outside the plane of the paper and going back in. So in this case, the p orbital, or the pi bond, is orthogonal to the purple pi bond, this one here. The pink one is going back and coming out, whereas the purple one is in the plane. And notice that in order to maintain the same sort of trigonal planar geometry in the sigma bond system, the carbon on the left, those two hydrogens have to be in the plane of the screen. So this hydrogen and this hydrogen are in the plane of the screen. This p orbital and this lobe and this lobe of this p orbital are going back and coming out at you, are inside and outside the plane of the board. So that gives you this overlap here with the pink p orbital on the central carbon. So essentially that gives us this shape for allene, which is sort of twisted, where the hydrogens these two hydrogens here are twisted 90 degrees from the plane formed by these two hydrogens. And so the plane formed by these two hydrogens and this carbon, this plane is in the board, whereas this plane is coming out and going in. So these two planes here are at 90 degrees, which is kind of an interesting shape for a sort of a very simple organic molecule like this, which is why allene is a little bit unusual.